Hey everyone, and welcome. You ever look at the world and just think, wow, it's messy, complicated? Well, what if I told you that a lot of that mess isn't really a mess at all? It's actually a combination of much simpler, hidden patterns. Today, we're going to learn how to unmix reality using a really cool statistical tool that finds simple groups hidden in what looks like total chaos.
All right, so here's our game plan. We'll kick things off with a pretty interesting puzzle, then we'll meet the statistical detective that can solve it. We'll see it in action, find out where it's already working in your world, and finally, we'll take a quick peek under the hood to see how the magic really happens.
So let's start with a mystery that data folks run into all the time. It's one of those situations where the data seems to be telling you one thing, but the real story, well, that's a whole lot more interesting, and it's hiding just beneath the surface. And this gets us to the big question, right? What if the data you think you're looking at isn't one single group, but actually two or three or even more different groups all jumbled together? And maybe more importantly, how on earth would you even know?
Okay, take a look at this. At first glance, this just looks like one big messy pile of data, right? It's got a couple of bumps, it's a weird shape, it just looks chaotic. But what if it's not one complicated group? What if what we're actually seeing is the result of a few different, much simpler groups all mixed together?
So how do we start untangling something like that? Well, we need a special kind of tool. Think of it like a statistical detective that can look at that jumbled mess and pick out the individual voices in the crowd. And that tool, that detective, is called a mixture model. So what is a mixture model, really? In the simplest terms, it's a model that starts with one big idea. It assumes the data didn't come from a single source. It's a mixture. The model's job is to then work backwards and figure out, okay, if this is a mix, what were the original ingredients? And this visualizes the idea perfectly. Instead of trying to fit one super complicated, squiggly line to the data, the mixture model says, hang on, I bet this is just a few simple, classic bell curves all added together. Each one of those nice, simple curves represents one of the hidden groups. So every mixture model has three key ingredients. You've got the components, those are the actual hidden groups we're trying to find. Then you have the weights, which basically tell us the recipe. Is it a 50-50 mix, or is one group way bigger than the others? And finally, you've got the parameters. Think of these as the unique fingerprint for each group. Its average, its spread, the stuff that makes it, well, it. Okay, I know this might still feel a little bit abstract, so let's make it real. Let's see how this actually works with a real-world example, because this is where you get that aha moment. So imagine you're a real estate analyst, and you've got this massive spreadsheet of house prices from across an entire city, but it's everything all thrown together. Tiny starter homes, downtown condos, huge suburban mansions. If you plot all of that, you just get a big, confusing mess. The puzzle is, can we find the hidden market segments in all that noise? This is where our model goes to work. It starts by making some initial guesses. Maybe it says, I think there are three types of markets here. Then it goes through every single house price and asks, okay, based on my current theory, which of these three groups does this house most likely belong to? It's this careful process of sorting and refining its guesses over and over again. And then, after a whole bunch of these guess and check cycles, boom, the magic happens. The chaos starts to separate into these clear, distinct clusters. You might see that one cluster is clearly starter homes, another one is mid-range suburban houses, and that third one is luxury downtown condos. The model has unmixed the data, and it revealed a structure that was hidden in plain sight the whole time. So now that you get the main idea, you're going to start seeing this everywhere. You'd be surprised how often you're already interacting with this kind of technology. Mixture models are the invisible engine behind a ton of modern tech. For example, when your banking app reads the numbers on a check you deposited, that's a mixture model trying to figure out if your handwriting belongs to the 3 cluster or the 8 cluster. Or when a news website groups articles by topic, that's a model treating each article as a mix of different word clusters. It's even how your phone's camera separates you from the background for portrait mode, by clustering pixels into two groups, you and not you. And they're used in some really high-stakes fields, too. In finance, models use them to spot the difference between a normal, calm market and a chaotic crisis market. In manufacturing, they look at sensor data from a jet engine to see if its vibrations belong to the healthy group or the about to fail group. They're even used in defense to analyze accuracy, separating the tight cluster of impacts from the scattered ones. So we know what these things do, which is awesome. But how does the computer actually find the groups? Well, the most common way is this really elegant two-step dance.
It's called the expectation maximization algorithm, or just EM for short. Now, it sounds super complicated, but it's really just a simple loop. First, there's the E step for expectation. This is where the computer looks at each data point and calculates the probability it belongs to each of the current groups. Then comes the M step for maximization. Here, it uses all those probabilities to redraw the groups, moving them and resizing them to be a better fit.
And that's it. It just repeats that two-step dance over and over again. Calculate the probabilities, then update the groups. Calculate new probabilities, update the groups again. And with each cycle, the answer gets a little bit better, a little more refined, until finally the groups stop moving. They've settled into their final best fit positions.
Now, there are a couple of different ways to approach this. The more traditional approach, on the left, kind of treats it like a treasure hunt. It assumes there's one single correct answer for each group's center and shape, and its job is just to find it. The Bayesian approach, on the right, is a bit more flexible. It treats everything as a range of possibilities, not just a single number. This can be really powerful, but it's also a bit more work for the computer.
And you know, what's so cool is that this isn't some brand new idea. The very first time someone tried to solve this exact problem was way back in the 1890s. A biologist saw that the shell measurements from a population of crabs didn't make a perfect bell curve. He thought it might be because the crabs were splitting into two different subspecies, and he got a famous statistician, Carl Pearson, to build the first ever mixture model to prove it.
So if there's one thing you take away from all this, it's this. Mixture models are this incredible tool because they operate on a really beautiful idea that what looks complex and random on the surface is often just a mix of simpler, more meaningful things underneath. They give us a powerful lens to see through the noise and find the hidden structures that actually make the world tick.
And that kind of leaves us with one last thought. Start thinking about the data you see in your own life. Customer reviews for a product, your commute times to work, even the songs in your favorite playlist. What hidden groups, what invisible patterns might be all mixed up in there, just waiting for someone to find them?